We now start our discussion on the last module, module number 4 of chapter 4. In 1944, in his text Functions of Real Theory, English mathematician J.E. Littlewood outlined 3 theorems which give the essentials of measure theory, and these are known as Littlewood's 3 principles. The first principle states that every measurable set of finite Lebesgue measure is almost disjoint union of finite number of open intervals. This is shown as a self-check exercise in the first 3 chapters. The second principle states that every pointwise convergent sequence of measurable functions is nearly uniformly convergent. Now, we have already seen this result, which is given by the famous Egorov's theorem. Recall that what we proved in Egorov's theorem? We proved that on a set of finite Lebesgue measure A, if we consider a sequence of measurable functions f n converging to a measurable function f almost everywhere, then given delta greater than 0, we can find a measurable set f subset of A with measure less than delta, such that on the complement A minus f, f n converges to f uniformly. Now, we come to the third principle. It states that every measurable function is nearly continuous, and in this module we will try to establish this particular principle, which is given by again a very well known theorem called Lusin's theorem. We start with the first result in this direction. Lemma 1. Let S be a simple function defined on open interval a b, then for any given epsilon greater than 0, there is a closed set f subset of open interval a b such that the restriction of S on f is continuous on f, and the measure of the difference, that is open interval a b minus f, is less than epsilon. We start the proof. So, for convenience, let us write open interval a b as I. Since S is a simple function, we know that it can be represented in canonical representation in this form: sigma I is equal to 1 to k alpha I chi e I, where alpha 1, alpha 2, alpha k are the distinct values taken by the simple function S, and as always E I is the collection of all those points where S takes the value alpha I. And we know that the sets E I are all measurable and are pairwise disjoint, and their union is the whole interval open a b. Now, since each set E I is measurable, so we can find a closed set F I subset of E I such that mu of E I minus F I less than epsilon by 2 k. So, for each I equal to 1 to k, for every set E1, E2, Ek, we get a closed set F1, F2, Fk, and we set F as the union I equal to 1 to k Fi. Evidently, F is a closed set and F is contained in Ei, and if we consider the difference I minus F, then it is clear that mu of I minus F, this is less or equal to sigma I equal to 1 to k mu of Ei minus Fi, and this is less than epsilon. So, here we again use the countable subadditivity of the Lebesgue measure. Now, if we take a point x from capital F, since F is the union of F1, F2, Fk, so the point x belongs to Fi for some I. Further, we have the sets Fi's are closed and pairwise disjoint, because Fi is subset of Ei and the sets Ei are already pairwise disjoint. Now, we can find an open interval J containing x such that J intersection F equal to J intersection Fi. Since S is the simple function which takes the value alpha I on the set Ei, and Fi is subset of Ei, so see that S takes the value alpha I on J intersection Fi. So, in other words, S is constant on the set J intersection F. This shows that if we consider the restriction of S on the set F, then being a constant function, it is continuous at the point x. Since this is true for any x belonging to F, so we get our conclusion that the restriction of the simple function S on F is continuous on the set F. Now, we move to the next result. In the last result, we have shown that given a simple function on open interval a b, I can find a closed set such that on that closed set the restriction of the simple function is continuous and the closed set is very nearly to the open interval a b in the sense of measure. So, in this result we would like to extend that result from simple functions to measurable functions. So, here is the formal statement: let f be a measurable function defined on open interval a b, then for any epsilon greater than 0, there is a closed set capital F subset of open interval a b such that the restriction of f on capital F is continuous on the closed set capital F, where as before the difference open interval a b minus capital F, this has measure less than epsilon. So, we start with a measurable function small f. Now, we already know that given a measurable function, we can always choose a sequence of simple functions which converges to that measurable function pointwise. We have seen this result in chapter 3. So, by that result, there exists a sequence of simple functions Sn, n belonging to capital N, defined on open interval a b such that Sn converges to f pointwise. Now, let epsilon greater than 0 be given. Now, for each n belonging to capital N, we consider the simple function Sn defined on open interval a b, and we can use lemma 1, the earlier lemma, on the function Sn. So, by the above lemma, we can find a closed set Hn subset of open a b such that the restriction of Sn on Hn is continuous on Hn, where as before open interval a b minus Hn, the difference set has measure less than epsilon by 2 to the power n plus 1. So, for each positive integer n corresponding to the simple function Sn, we get a closed set capital Hn with the above property. So, let us take capital H as the intersection of all these sets Hn. So, H equal to intersection n equal to 1 to infinity Hn. Since H is intersection of a collection of closed sets, so H is obviously a closed subset of open interval a b, and if we consider the measure of open interval a b minus H, then it is less or equal to sigma n equal to 1 to infinity mu of open interval a b minus Hn by the countable subadditivity of the Lebesgue measure, and this is less or equal to sigma n equal to 1 to infinity epsilon by 2 to the power n plus 1. So, this sum is equal to epsilon by 2. Again, since Sn converges to f pointwise on the measurable set capital H, of course, H being a subset of open interval a b has finite Lebesgue measure. So, we can apply Egorov's theorem on this particular sequence of functions, and applying Egorov's theorem, we can find another closed set capital F subset of H such that mu of H minus capital F is less than epsilon by 2, and Sn restriction on capital F, this sequence of measurable functions converges uniformly to the function f on capital F. So, if we combine the two observations, then we have measure of open interval a b minus capital F. This is again less or equal to mu of open interval a b minus h plus mu of h minus f, because open interval a b minus f is equal to open interval a b minus h union h minus f. So, we again use the sub additivity of the Lebesgue measure, and the right hand side is again less than epsilon. Observe that as each restriction Sn on capital F is continuous on the closed set capital F, and this sequence of functions converges to small f uniformly on capital F. So, the restriction of small f on capital F is continuous on capital F, because we know that if we get a sequence of continuous functions and if it converges uniformly to a function, then the limit function is continuous, and this completes the proof of this result. So, now we are ready to prove our main result, but before that we need a result from general topology, which we will use to prove our desired result. Now, this is an extension theorem. The theorem states that if capital F is a closed subset of real numbers and small f from capital F to R is continuous on capital F, then there is a continuous function g from the whole real line to real line R to R, such that f equal to g on capital F. That is, any continuous function on a closed subset of capital R can be extended to the whole real line to a continuous function. So, we have now the very important theorem, Lusin's theorem. It states that if f from R to R is a measurable function, then for any epsilon greater than 0, there is a closed set capital F and a continuous function g from R to R, such that f is equal to g on capital F and the set f complement has measure less than epsilon. So, this shows that a measurable function is nearly continuous. We now start the proof. First, observe that we can write the whole real line capital R as union of countable number of open intervals I m union capital N, the set of positive integers, where I m is the open interval m m plus 1 for every positive integer m. Now, also observe that capital N being a countable set has Lebesgue measure 0. Now, we consider each open interval m m plus 1, that is I m, and consider the restriction of f on I m. So, the restriction f on I m, this is a measurable function on open interval I m, that is m plus 1, and we can use the earlier lemma to this function. So, given epsilon greater than 0, we can find a closed set f n subset of I n such that the restriction of f on this set f n closed set, it is continuous on capital F n, and the difference I n minus f n, it has Lebesgue measure less than epsilon by 2 to the power n. So, for each positive integer n, we have got a closed set capital F n subset of I n, which is open interval n plus 1. Now, set capital F as the union of all these closed sets, that is union n equal to 1 to infinity f n. Observe that capital F is a closed set, and if we consider mu of f complement, then this is less or equal to sigma n equal to 1 to infinity mu of I n minus f n plus mu of capital N, again using the countable subadditivity of the Lebesgue measure, and this is less or equal to sigma n equal to 1 to infinity epsilon by 2 to the power n, and this sum is equal to epsilon, because mu n is already 0. Now, if we consider the restriction of small f on the closed set capital F, this is continuous on the closed set capital F. So, by Tit's extension theorem, there is a continuous function g from the whole real line to R such that f equal to g on capital F. That is, we extend the continuous function small f on capital F to the continuous function g, and this function g is our desired function, because see that g being equal to small f on capital F is continuous on capital F, and we already have mu of f complement less than epsilon. So, we have this particular result, we again repeat it, that whenever we have a measurable function f from R to R, then for any epsilon greater than 0, I can find a continuous function g from R to R such that the measurable function is equal to the continuous function on capital F, where f complement has measured less than epsilon. So, to summarize, in the last module, module 4 of chapter 4, we have again proved a very important result on measurable functions, which is given by the Lusin's theorem, which states that every measurable function is nearly continuous. And with this, we end this module as well as this chapter.